Well, in the last section of chapter 4, we left off with doing a little thing called an integral. We were trying to find those antiderivatives by using a process called integration. And all that chapter 5 is really focusing more on what integration is. And specifically, we know what it does is kind of reverse the whole derivative. If we found the derivative of a function and we want to go backwards, we take the integral of the function to get back to the original one. Okay? Well, there's a big key with integration also that really comes in big handy. It's like with the derivative, it's great because it can help us find the slope of an equation. Well, the thing with an integral is that we can help us find the area underneath the curve or the volume underneath the curve. Okay, so it's just area and volume of specific shapes. And the way we're going to first start talking about it is through breaking it down. Okay, if I give you a curve, and how we're going to look at it is we're going to break a curve down into an object that we know we can take the area of, like for example, a square or a rectangle, because the area of a rectangle is just the length times, or the one side times another side, which in this case would be like this lower side times the height. Okay, and so what we're doing is we're going to be taking a normal curve, like this whole curve, something that we don't know the area of the formula for the area of it, and we're going to break it into these boxes, where every time I break it into a box, if you want to consider this the width is always going to be the same no matter what. Now, obviously, because you can't fit a rectangle inside of a curve, we're going to be either overestimating what our actual area is going to be or underestimating it, but we can kind of get a really good general idea by doing this process. When you go through the process of finding an upper sum, what you're going to do is get a little overestimate of everything, because we're going to be creating rectangles that kind of go just above the curve. You see how they're just going above? Whereas if we go with the lower sum, what we're doing is we're fitting rectangles within the square or within the parabola or whatever shape we're finding. But again, this distance right here will be always the same no matter what. That's the key. And I know it might not look that way on my notes, but that's what I was trying to go with. And then all we're going to use is the height of these also to help find the estimate of what the area for that parabola is going to be. And then also there's that third rule where we get the actual midpoint between the two. So it's kind of a halfway between the upper sum and the lower sum. Okay. So let's take these concepts and let me show you how to do this in example 1. In example 1, I kind of wrote out the main formula. Because remember, the formula for to find the area of a rectangle is basically the length times the width, or in this case, if we want to look at it as a length maybe times a height. Delta x is going to represent your length. F of x1, remember that's a y value, so that's your height. So it's going to be basically the length and height of one rectangle plus the height and the length of a second plus however many you want to go on. Okay, and specifically for this function right here, we're looking at 4 minus x squared from negative 2 to 2. So we're looking at trying to find the area under the curve between negative 2 and 2, going up to 4, and we're going to find it basically in 4 different ways. 2 ways with a lower sum and 2 ways with an upper sum. So let me go on here and draw you what it's going to look like with the lower sum. Okay, so the first part, we want to find the lower sum, and we want to do it with 2 rectangles. Okay, well obviously, if I'm going to go from negative 2 to positive 2, and I want to divide it into 2 rectangles, then the base of one rectangle is going to go from 0 to 2. And the base of the other rectangle is going to go from negative 2 to 0. Okay? Now how you do the lower sum? We need to create basically 2 rectangles that stay within the function itself and that have this length of basically 2. Okay? So in a sense, up there in the formula, if we want to find the area, it'll be a function value for the first delta x, which in this case is a length of 2 units, plus a second y value for another length, which is just 2 units. But here's the thing, the only way I can start out here on the outside and fit 2 rectangles in here that still stay within the actual parabola itself is, in other words, what I'm saying is there's no way to do it. They're going to have to basically be almost flat rectangles. When they're flat rectangles, they don't have any height to them. So really these f values here are going to be 0 times 2 plus 0 times 2. So we're going to have an overall area value of just 2 when we do a lower sum of 2 rectangles. Now let's look at this exact same thing though. Let's find a lower sum when we have 4 rectangles, and y'all can see the difference. So let me update my graph for just 1 second. Okay, so what I did, come over here to this graph real quick, is I went in there and I created 4 rectangles of equal width. Obviously, if you're going to divide the interval from -2 to 2 into 4 equal pieces, it's going to go by 1. So -2 to 1 is 1 rectangle, -1 to 0, 0 to 1, and 1 to 2. Okay, and in that case, the delta x, the change in x, is going to be 1s. So I went into the equation, and so it's going to be a height times the width, which is 1. A height times the width is 1. Width and width, okay? So always the delta x's are going to be now 1s when you're looking at 4 rectangles for this specific example. Now, so in order to get the height values and to fit 4 in here, you draw a line that goes directly up until you touch the graph. See, at 2, I can't just draw a line and up and touch the graph because I'm already there. So that's why it also kind of shows you how in the first one, in part A, on the lower sum with 2 rectangles, we really couldn't do anything because the outside portion, the outside width of that base was 2 and you're already on the graph. Whereas at 1, I started at 1 and I went up until I touched. At 1, I also go up until I touch, and then at 2, I'm already touching, okay? So here's 1 triangle, there's 2, rectangle, and there's 3 and then 4. Now to get the height, that right there, all I'm going to do is plug 1 into my equation. So 4 minus 1 squared is 3, it has a height of 3. 4 minus 1 squared has a height of 3, okay? And then plugging this in, that means then, going back to our area formula, that f of x value is actually going to be then that y value at, let's say, -2, which is 0, times 1, plus the height there at 1 or at -1, which is 3, another height which is 3, and then that last height was 0. So overall, this is going to equal 6. So the answer for when we're doing a lower sum with 2 rectangles is 0. For a lower sum with 4 rectangles, it's 6. Okay, so now let's take this exact same concept though and do an upper sum. The difference with the upper sum is now we're going outside of the parabola. So let me erase this and get some new parabola drawn for us. Okay, so to start out with part B, what I did is I divided it into 2 parts. We're going to do an upper sum with 2 rectangles. So I'm looking at adding 2 rectangles, 1 and 2 right there. There's the height, and then this is the base, the length of the base, which if it's going to be 2 rectangles, our bases are each going to be 2 equal lengths. And there's the height of the second rectangle with a base of 2. And then we're going to do it again with 4 rectangles where every base is 1. So there's showing in there that every base is single 1. Okay, so let's focus on the 2 rectangles though for a second. And how the upper sum works is go to your point, and we're going to now go outside the function. And then we're going to, until we get even with the graph, and then we're going to come over. Okay, so there is 1 rectangle to represent area, and then we're going to do the same thing over here, and there's your second rectangle. Okay, so basically it's like, what is the height right here? If I go from here to here, what is the height? Well, obviously the height is 4 because we're going right to this peak right here, or you can plug it in the sense of that dot, so we're going to go up and over. We're doing upper sum, so we're going to plug this dot into our equation, and 4 minus 0 squared is just 4. So going to our formula, then the area is going to be 4 times 2 plus 4 times 2, which is 16. So this is 16 is the answer for the upper sum whenever you have a rectangle, 2 exact rectangles. Okay, so let's now do the same thing when we divide it down into 4 rectangles. Okay, so with 4 rectangles, we've got our lengths happening at -2, -1, 1, and 2. You know, those were going to be the bases basically of the 4 rectangles. We're going to start on the outside and go from the outside. And we go up until we hit. The same thing with that one. We're going to go from the outside and go up till we hit the graph. And the same thing over here. Okay, so we want to know what are these points that we're touching the graph at. Well, this is at 1. So when I plug 1 into my equation, remember that height right here from here to here, the height right there is 3. I'll put in 3 in there. The height of this one, if I plug in -1 into my equation, remember the height is 3. And then here, for either of these two, the heights are 4. Okay, So then going back into our area equation, the height of the first rectangle is 3, the width is 1. The height of the second rectangle is 4, the width is 1. And then again 4 with the width being 1, and then again 3 with the width being 1. So overall area, when you're doing 4 rectangles and doing an upper sum, it looks like it's going to be an overall area of 14. Okay, so now this is just a long formal way of doing this. We're going to learn a shortcut. It's not going to be in this lesson. We're eventually going to learn a shortcut. This is how to do it. But remember, the lower sums have to fit within the actual parabola, and the upper sums can go outside the parabola.